Okay, well, welcome everybody. So today we are going to continue working on material that you read about, basically coming up with numerical approximations for solutions. So we've been talking about how we can graphically approximate solutions using slope field, and now we're going to kind of equate that to a numerical process. And then on Wednesday, we will start thinking about how we can solve them exactly, finding formulas for solutions. So just so you're aware, my plan is to have the materials for the week uploaded by Mondays. So you should have seen a bunch of stuff get uploaded over the weekend for week 2. So all of the materials for week 2 are over here. Things for Monday, things for Wednesday, and these are the assignments for this week. So thanks for the quizzes today. You have another brief quiz before class on Wednesday. And then don't forget, your first homework assignment is due tonight. Homework 2 is going to be due a week from today, next Monday. Okay, any questions about that? Okay, so then let's, so we're going to be working with that worksheet. Let me just show it to you, sorry. Over here for called Euler's method. That's what we'll work on today. So if you want to download that or get that handy, go for it. And this is the worksheet we'll be working on in class together on Wednesday, if you want to download that too. Okay, so if you've got that worksheet open, hopefully you're looking at something similar to this. So we did basically, the videos went through mostly the second page of this worksheet. So I just want to think about this model and give you a chance to ask any questions about what you might have read or watched. Is there a question? I think I heard a voice.
Yeah, where can you find that worksheet at in Canvas?
It is in module 2, the module for week 2, I should say. And I think the first section in week 2 are the readings, and then the second section are materials for Zoom class, and it's the worksheet for Monday, which is called worksheet 4, Euler's method.
Thanks.
Okay. So we've been thinking about, as our kind of motivating example, thinking about population growth, population models. So let's kind of stick with that theme. So let's assume that we've got P is a population, say, of fish. And we're going to measure this, say, in thousands. So when we say something like 10, we're going to think about this as 10,000. So we're going to think about P as thousands of, in this case, fish. And so we've been working with models where we've been assuming that there's no competition, unlimited resources, etc. And this was the model that we were using. This is called an exponential model, and it's not a very good model in general for long-term predictions of population growth. So you do want to take into account that there are oftentimes competition for limited resources. There are things like spreading of diseases when you get overpopulated. And there are other things that might cause populations to decrease. And so in question 1, and today we'll start by thinking about this model over here. And so the first question is, how does this model possibly account for limited resources and other things that might cause populations to decrease? And so if you've got some thoughts on that, you're welcome to share it. Or if not, I'd like some chat responses at least. You can chat them in directly to me. I'd just like to kind of see how you guys are reading these differential equations. So does anybody have any suggestions about why this model would actually take into account decreasing populations once they get too large?
It's the one part that says 1 minus p over 10.
Sorry, say that again, Eric. I missed that.
The one part that says 1 minus p over 10.
Yeah, and so keep in mind that dPdt, that's measuring the rate of change. So positive slope means population goes up. If dPdt is negative, that's going to tell us that the slope goes, that the quantity is decreasing, that is going down. So we can see over here, yeah, this term is always going to be positive. So in some sense, what we're saying, this is kind of capturing that when there's a lot of people, they reproduce faster. The more population is good for some things, but it also leads to competition for these limited resources. And so this factor can be positive. Say if P is between 0 and 10, but it also can be negative if P is bigger than 10, right? So if we plug in a value like 20 in for P over here, then that would give me 1 minus 2, right, which would give me a negative quantity. So that second factor is saying, well, if P gets pretty large, then, oops, sorry, we might actually get some negative contribution from that second factor. Okay, any questions about that? And in case you're kind of curious, we'll take a look at these models in more detail. But this is what would be called the logistic model for population growth, which is typically much, much more accurate. Okay, so let's think about this initial condition. If we start at time 0, say with 10,000 fish. What's kind of special about this value 10?
It gets us to our asymptotic line.
Yeah, so what do we call this type of solution? Has a special name, right? Then we know what we would call this solution. So what would I get if I say want to calculate the slope of the solution that passes through this point? So we can think about, here's our slope field. We've got T, we've got
This would be 0.
Say that again, sorry?
If the initial condition of population is 10 at time 0, then the slope dP/dt would be constant. It would be 0. So then it would be a constant solution, maybe. I don't know what the word is, though.
Yep, you got it. So when I plug this point 0, 10 into the differential equation, well, there's nowhere to plug the t value. But when I plug in 10 for p and calculate this, we would get a slope of 0. And so on the slope field, right, we could draw a little horizontal line there. And then remember, like, this is an autonomous system, right? There's no independence on the time variable here. So I know that for any point that has a p-value of 10, the population would not change at that point. So we have a constant solution. And I can actually draw what that solution looks like in here. So this is a constant solution. Okay, if we start with 10, then p is going to stay constant at 10 forever. So that's kind of what we would call, one thing we would call it is an equilibrium solution. Right? So remember, equilibrium solutions are constant solutions. These are solutions that when we plug them into the differential equation, we should get 0 for dP/dt. And in the case of population growth, in case you're curious, we would call this the carrying capacity. What that means is that's like the largest population that this ecosystem could support. Well, I guess I'm jumping to a conclusion there, but we'll see that. Okay, any questions about that? Okay, so I will skip opening the slope field viewer since I've got it on the next page of the sheet anyway. But if you're ever curious about playing around and trying to get pictures of slope fields, you can use this app. This is a GeoGebra app to view them. So if you were to enter this into GeoGebra, you would see something like this. Okay, so here's the slope field for that differential equation. And what we just saw is, right, here's this solution corresponding to the equilibrium at p equals 10. And this will kind of relate to some of the stuff that's on your homework assignment that's due tonight, but relating to some of the stuff that we talked about last time, this is an autonomous differential equation. So we can set up what's called the phase line for this, which is basically saying that since once I know the slope for a value of p, it's the same all the way across. It's like condensing the slope field onto a line. So we would mark our equilibrium over here. Right, so we could identify that this differential equation has two equilibrium. P of 0 comes from the fact that when I plug that into the first factor, that would make dp dt 0, and 10 comes from the second factor. So when we're setting up these slope fields, or excuse me, these phase lines, we first mark the equilibrium values on that vertical line. And then we indicate whether dp dt is positive or negative by placing arrows on that line. And so we can see from the slope field that our phase line would go down over here since dp dt is negative. It would go up over here since for all of these values dp dt is positive. And so what's not included is any information about what's happening when p is less than 0. Oops. Starting with this equilibrium at 10, that's an equilibrium. Would we consider this, how would we describe that equilibrium? Let me just say that.
Stable.
Yeah, so this is stable. What this is saying over here is that if we started with a population that's bigger than 10, it's going to decrease and it's going to look like this. But it's not going to decrease forever. It's going to flatten out and approach this equilibrium solution. And if we start with a value for the population, which is between 0 and 10, this one would increase. So what we can see is for any p-value, that as t goes to infinity, not 0, as t goes to infinity, our solutions are all going to approach 10 as long as p is positive. So we would call this exactly stable. And the missing arrow that we haven't completed yet is down here. It doesn't practically make sense to think about a negative population of fish, but just for the sake of the mathematics, we'll consider it. So if p is negative, what's going to be the sign of the derivative dp dt based on the differential equation that we have up here. So if you think it's positive, give me a thumbs up. If you think it's negative, give me a thumbs down. If you think it's 0, give me a 0. Okay, yeah, so that's going to be negative, right? Plugging in a negative value of p, this first factor would be negative. This second factor is going to be negative, positive. And that's what gives us a negative times a positive, which makes it negative. So down here, the arrow should be pointing down. So these solutions would look like this. And so this equilibrium over here, because if we start close to 0, but not exactly at 0, the solutions head away from that value. We would call this an unstable equilibrium. And so if we start with a value less than 0, then a limit of these solutions, we could say, does not exist. They're going to keep going down forever. And practically speaking, that doesn't really make sense, but it's good to just think about the behavior of these solutions in theory. So that is a bit of review about autonomous systems and phase lines, not quite about numerical approximations. But any questions? So your last homework assignment is going to, your last problem on the homework due tonight should look pretty familiar to, similar to this one. Okay, so let me back up. So I'll just say, we kind of answered this question on the other page. We haven't talked about question number 2, and this is really the topic that I want to talk about today, which is how can we use information about the derivative to come up with approximations for our population. And if you looked at the video, then hopefully a lot of those ideas are just, you know, a review of things that you might have talked about in calculus. It's like linear approximations in some sense. So if I know that at time 0, my population of fish is 2,000. And we want to approximate how many fish are there in 2 years from now, if that's what we're measuring T in. Okay, and so we don't necessarily have a solution to this differential equation, but still we can use the differential equation to say something about solutions, just like we did with the slope field. And so the way that this was described on the video was we can calculate using the derivative approximately how much is the population going to change, and then we just add or subtract that change to the initial population that we started with. So the delta P that we have here, I should say more precisely, we can approximate it by taking the derivative, say at time 0, and then multiplying it by the change in time. Right, so the derivative, one way that we can interpret that value, we could say that the derivative tells us every time you increase the input by 1 unit, approximately how much is the output going to go up. And so if we increase it by 2 units, then we would just approximate the change in P by multiplying the derivative by that 2 unit change. And so in this case, this change would be the 0.48, the derivative at 0 times 2, and that gives us 0.96. So that's telling us that the population is going to increase by approximately 0.96 thousand fish. In other words, 960 fish. So we get an estimate for that population to be 2.96. Okay, which if we're thinking about this in terms of thousands, that could be 2,960. And so those were the types of questions that you had to do on the reading quiz. But any questions about that? Okay, so what I'd like to do now is think about how this tail to tip method works. So I'm going to just clear out some of these solutions that I drew in over here. I'll leave the phase line over there. And I'll leave the equilibrium over there. So I just want to illustrate what it is that we just did. So we started with a population, P of 0 was 2. And what we wanted to do was then approximate what the value is on the solution when T is equal to 2. So we kind of assumed that our slope looks like this. And then we stop it over there. So what's going on in this picture is down here, we have that delta T was equal to 2. And over here, this is telling me that the change in P was approximately the slope times our change in time 2. That's like the rise. And then we add that change to the initial value of 2, and that gave us like our 2.96. And what we're doing when we do this tail to tip method is, okay, we want to say approximate what is the population of fish 4 years from now, 10 years from now, whatever. We want to take this out further. The further we take this out, the worse our approximation gets, right? These derivatives are local measurements of rates of change. So the rate of change in year 0 really isn't going to be too much a great predictor for the rate of change 10 years from now. So this tail to tip method says, okay, pick a small value for delta T. And we can kind of argue whether delta T equals 2 is small enough. Probably not. But we could think about this method and then just reapply it with smaller values of delta T. So I go out for a small value of a small change in time. I use this method to approximate the next value of y. And now rather than use the slope at time 0, I recalibrate my slope after year 2. And so then over here, rather than use the slope that we had at the initial point, I'm going to use the slope that we have over here, which is a little bit flatter. So I take that out for another 2 years, get my next approximation, and just continue this process step by step by step. Okay, so we would repeat the same process. We just now would have a different value for our derivative that we would update.
When we're doing these approximations, the smaller the change in time, the better it would be. So what's a good kind of method, rule of thumb for choosing the change in time? Because you could do that with like 0.2 years too, and you could still do it. It would just
yeah, so I'll just say this, you're right, and we'll get at this idea in a bit, but yeah, the smaller we make this change in time, the better our estimate is going to be. So I'll just say that's the main rule, right? The smaller you make it, the better. Sometimes you're limited by your technology as far as how small you can make that change. For the purpose of this class, I'll tell you what to use. But I'll also say there are some ways that you can calculate the error in this approximation. And so sometimes you might want to say, like, what's the maximum amount of error that I'm willing to accept? And let me pick a value for delta t that's going to ensure I have less than that error. Okay, and so kind of just to summarize what might be wrong with this method is exactly this fact that we can see from the slope field that the derivative is constantly changing. So when we assume that the derivative is constant over, even if it's a small period of time, that's an incorrect assumption. But yeah, the smaller we make that time, the less error that we might be introducing. Okay, questions? So I'm gonna break us up into smaller groups now, and in the groups I would like you to discuss the next set of problems. So yeah, over here I just made a little change. So this is a similar looking model. I just want you to be clear that it's not the same one that we started with, right? We don't have that 0.3 in the front, and we now have p over 20. But what you should be thinking here is this one would have two equilibrium solutions at p equals 0 and p equals 20. That's not really at all what this is asking us, but it's just worth to make that note. But this one is asking you to try and think about how we could come up with these approximations without using the slope field. We don't need that picture to motivate our example. So I'm gonna break you up into groups, and you guys can talk about what these people are doing when they're trying to solve these and which of them do you think is best. So I'd like you to get through 5, 6, and 7 in your groups if you can. And if you guys wrap that up and you want to try question 8, then go ahead and give that one a shot. But we can do question 8 together if you don't have time to get to that. But any questions before I break us up? Okay, welcome back. I think everybody is back in. Great, so thanks for your nice work with your classmates. So I just want to say that I don't know what Zoom looks like, particularly from the student point of view, but when I close the breakout rooms, you don't have to come right back here. You have 1 minute to kind of wrap things up. So just keep that in mind. But if you're done with your group, then you're welcome to come back. So, okay, so let's compare our results on these sorts of problems. So I think checking in with the groups, you figured out the algorithm here about what is going on. And so what's happening is we are using this 10 just to kind of feel how this algorithm works. We plug in our coordinates for our point into the differential equation, and that gives us 5. And then we look at what is the change in t, which is 0.5. And so that allows us to either scale up or down what the change in p is going to be. So it might be helpful sometimes to make an additional column over here. Maybe you can just do it in your head to keep track of that part of the process of scaling the change up or down. And then we add that change to the 10 and we get 12.5. So without kind of belaboring this one, I'll fill in some of the answers here, and feel free to ask away. So let's see. So this one should have given us a, the PDT is like 4.6. I'll just abbreviate, estimate it like that, 4.688 around. And then we would use that information to calculate the change in P by scaling that in half and then add that to 12.5. And that gives us approximately 14.844. Calculate the slope. Again, that should come out to about 3.827. And then we calculate our value for P using that rate of change. And then we've got our estimate over here. So we actually don't care about the slope at that point because that's where the process stops.
Professor,
Yeah.
I actually don't see how you got 14.8. Wouldn't you add the 4.69 if you're rounding?
Oh, yes. I might have, do I have a mistake here? Maybe I do. Yeah. So the 4, I think I just put some, excuse me. So what did I get wrong here? Did I get the right slope? Sorry.
Should we be adding 4.688 to the 12.5?
No, I'm sorry. I think this is okay, right?
Yeah, I think you divide it by 2, right?
That's right. Yes. So you would take that 4.688, divide it by 2 because the change in time is 1/2. So we're actually going to add half of 4.688 to the 12.5. So yeah, that's what would kind of go over here. Would be, we have the 4.688, and then we multiply that by 1/2, and that gives us our change, which should be about 2.344. And that's what we add to the 12.5. Okay, any questions? So just to try and like summarize this, kind of what we're doing is we kind of use the initial point to calculate the slope. Then we find the change in P by taking the derivative and multiplying it by the change in time. And then we get our next point by adding delta t to our initial time, and we calculate our next population by adding delta p to our initial population. And then we repeat. Instead of using the initial value, then we use our updated point to calculate dp dt, find delta p, and then add those values. Any questions? Okay. Does somebody want to take the mic and help me finish up this table for number 6?
I guess I can go.
Okay, thanks, Shamek.
So for the P column, I got 13.71 and 15.86. And for the dp/dt column, I got 4.92, 4.31, and 3.28.
Okay.
Which I guess doesn't matter.
That's right. I mean, if we wanted to go one more step, yeah. So it really depends on like, yeah, what are they asking us to approximate? So in this case, if they were asking us to approximate the population and time is 0.75, this would give us that approximation. Did groups get something different than that?
Yeah, we got something different.
Okay, why don't you help me out?
Well, it the change is a fourth. The time is changing by a fourth, so it's not a half.
Oh, yeah.
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 So
So this change over here should be, well, this one was done, right? So they took 5 and multiplied it by 0.25. That comes out to 1.25, and that was added to the initial population. So then at this stage, we would, I think the slope is okay, right? That's 4.92, that looks fine. It's just the actual change in P now is gonna go up by 1/4 of that because we're only changing time by 1/4 now.
Is that first one 12.41 then?
Yeah, so let me just update these. So the next one is, yeah, this one would be about like 12.48. And then we would use that value to update the slope, dp/dt, which I'm using my calculations here. You can double check me, comes out to something that should be about 4.7. You multiply that by 1/4. And that's going to tell you what the next change is. And that would put us over here at about 13.65. Does that match what you guys got that we're multiplying by 1/4 or less?
yeah.
Okay. Yeah, so this one actually should be about 13.65. Yeah, so definitely be sure that it's the same process that we did up here. It's just in this case, we now use 0.25 for our delta t. Any questions? So in comparing 6 and 5, your answers in 5 and 6, which approach do you think is more accurate? Go 5 or 6? Okay, and so why is 6, Abraham?
I guess 6 would be better because there's smaller increments of change, and with the smaller increments of change, the 0.25 change, it's accurate because the slope is always changing in the dp/dt function, and with the smaller amounts of change, we have less of a change with the slope. Each like the constant slope is changing each time to a better extent. I don't know if that makes sense, but basically in the dp/dt, it's always changing all the time, and with the not deep, the smaller ones, we get a better, closer approximation.
Yeah. Yeah, so the difference here, it's not that they're doing a different approach, it's just that they chose a different delta t value, right? And the more frequently we update our slope, the more accurate this is going to be because the slope is changing all the time. Yep. Any questions? And kind of one interesting thing is this slope field would look pretty much the same. The solutions here are going to look very similar to the first example that we looked at. Except the equilibrium value now is 20. And so we were approximating what happens when we start off at this point over here at time 0, our population is 10. And what we can see is that it's going up, right? But it's going up by less and less and less. And at some point, we should see our values start to flatten out close to 20. That's what we would expect to happen. And so for a case like this, we would say that this graph over here, let's take it up to the next level. What could you tell me about the sign of the second derivative for a graph that looks like this? Would that be a second derivative positive or a second derivative negative? So let me ask this. What about this graph that I just drew over here? Is this concave up or concave down?
Concave down, right?
This is concave down. That's right. So down is the thing that looks like a frown. And so our graph kind of looks like this thing over here. It's going up, but it's flattening out. So when something is concave down, the second derivative happens to be negative, in case you're kind of curious about that. So this has some effect on whether our estimate is going to be an over or an under estimate. And so when our graph is concave down, our estimate is going to be an over estimate. Always. And when the graph is concave up, our estimate is going to be an underestimate. And that's just relating to this idea of when you have something which is concave up, the actual graph actually should be below your tangent approximation for that graph. Just some related facts to this. Okay, so let's see what happens on number 8. And so number 8, the thing that we want to be careful about here is that this differential equation is no longer autonomous. So this is, this depends on both variables y and t. But that doesn't really affect much. So here, what we want to do is we're going to come up with an approximation for the value at 1.5. So I'll set up my table to think about these. I've got at time 0, 0, 4. And yeah, for those that were doing this, you could have chosen different values of delta t since that wasn't given to you. I'm going to choose so that this doesn't take forever. Or actually, did somebody calculate this? I want to share what you did.
Sure. I just did half
Okay.
increments of t, and then you just add them together to get dy dt, and then you do the same thing of adding a half of that to the y, or to the p value, I guess.
These are Y's. Thank you.
Yeah.
Yeah. So at the first stage, we would say that dy dt is, what did you get for that, Brian?
4.
4, and therefore, what's the approximate jump in y?
2.
Would be 2. And this is equaling the derivative dy dt times what we chose as the change in time. So this comes from taking the derivative, which is 4, and then multiplying it by delta t, which is 1/2. Okay. So at this stage, we see that y is going to increase by approximately 2 units. So therefore, what's next?
You add the 2 to the 4,
Mhm.
so then you put a 6 in for the 0.5. Yeah, that one.
Mhm.
And then you do dy dt again, which is just 0.5 plus 6, so it's 6.5.
Mhm.
And then you do the half again.
Yep.
And then you just plug it in again, add that to that, add those together, and multiply by half.
Very dangerous doing math in my head, yes?
Yeah, yep, and then, yeah, just add it back down.
Okay, and this would give us 14.375. Yep.
And then the
Yeah,
next.
and then we could stop, right? That's all.
Oh yeah, yeah.
Now we've got at 1.5 using this method, y is approximately 14.375. And I'll just say that any first order differential equation, so any differential equation that only has first derivatives in it, we could actually use this method. There's almost no point in learning how to solve first order differential equations because computers are so fast at doing these numeric approximations that you can almost numerically approximate any of the ones that we're going to think about solving exactly on in the next class. But this method doesn't work if you have a second order differential equation because we need to know the first derivative in order to approximate these changes. So that was a little bit quick, maybe filling in this table. And any questions? Okay, and in case you're curious, this is section 1.7 of the reading materials. Deals with this method. Okay, and so is this exact or an approximation? Exact or approximation?
It's an approximation.
Okay, good. All of these things are approximations, right? Since the rate of change is always changing, and we're making this assumption that it's only changing every half a second, right? Okay. And so lastly, let's kind of generalize this process that we've been doing, that we outlined before. So I'll just kind of start this general formula by saying, okay, if I want to calculate the next approximate y value, I take my previous y value and then add to that what I'm estimating the change in the output to be. And so really what I just want to fill in is how are we calculating this change in output? So what things do I need to know in order to calculate delta y or estimate delta y?
The derivative and the change, the time value.
And here I just want to be certain that we're picking the derivative from the start of that time period. That's right. So that's what that y prime previous means. Yeah, so we can summarize this. Maybe it's more commonly written with indices. Like this. And this is what is called Euler's method.
Okay, so this is an approximation. So say we're going to the moon and we need really specific values. Will there be a way to like measure the difference of it? Because like we all know that the answers we got aren't the true answers, and that might cause the rocket to blow up. So is there a method to like say like how small does it have to be? How close does it have to be? Is there a way to test that? If that makes sense.
Yeah, so if you're going to the moon, let me just say a couple of things about approximations is that, yeah, like if you are approximating each intermediate step and then getting a final answer based on a whole series of approximations, I'll just say that your error gets compounded if you're approximating each part along the way. It also is going to get more severe the further out you want to send this approximation. So I would say in things like going to the moon, you really don't want to approximate too much, but they might have like a window that says, okay, as long as like we can have a speed like when we're landing on the moon, which is within epsilon of what our target speed is, will be okay. And then we can determine how often we want to do some sort of approximation to make sure we're underneath some error threshold. But I'll just say that this stuff, usually we're pretty good at solving things and getting people where they need to go in, or objects where they need to go in space. But there's like a very common example of when this stuff goes bad, and there was the first Mars rover that was sent there. It's been a while now, where they did all of the calculations in the wrong system. So they did them in metric system, and then they were somehow incorrectly converted to, British standard system, and it crashed. And it was not a success. That was a very, very expensive crash. Then they caught that mistake and were successful on the next one. Yeah, so this is really important to try and get as precise if you're projecting that for a long distance. Yeah. Okay, so I'll stop here since we've hit the end of class. So for Wednesday, we'll start solving these, which means we're going to start integrating things. So part of the theme of the quiz for Wednesday is reviewing some integration methods. In particular, integration by parts, integration by substitution, and I put a whole module in Canvas called Integration Review, which has some sections out of a calculus book that I author that could help you. So I have kind of a section that describes these things, their problems at the end of the section, and I put solutions to those problems as well. So I would definitely encourage, this is a good time to start practicing reviewing integration before we start integrating things in class on Wednesday. Okay, thanks everybody, and have a nice afternoon. Don't forget about the homework, and otherwise I will see everybody on Wednesday. Yeah, and if you have any questions, just happy to stick around for you. So if not, see you later.
Thanks. Have a good day.
Yep.